An exposed ground wire can indeed cause electrocution under specific circumstances. If a ground wire is damaged or corroded, its capacity to safely divert current from electrical equipment diminishes. This compromised wire poses a significant electrical hazard. Secondly, if the exposed ground wire makes contact with a live wire, a pathway is created for electrical current to flow through the ground wire and subsequently through any person who touches it. This situation represents an immediate risk of electrical shock. Thirdly, a high resistance grounding system, whether due to improper design or inadequate maintenance, can also elevate the risk of electrocution. Such a system may restrict current flow through the ground wire, increasing the potential for dangerous electrical exposure. A tingling sensation in the hand often indicates an electrical shock or electrocution resulting from electrical current passing through the nerves. Even a mild electrical shock should be treated with caution, as it can lead to more serious injuries. In the scenario of the kitchen worker experiencing a tingling sensation while hosing down the kitchen with an exposed ground wire surveyor steamer, several factors could have contributed. Firstly, the ground wire may have been damaged or corroded, reducing its effectiveness. Secondly, the ground wire may have come into contact with a live wire from the steamer, creating a hazardous current path. Thirdly, the grounding system itself may not have been properly designed or maintained, failing to provide adequate protection. To mitigate these risks, several recommendations should be followed. Firstly, a thorough investigation of the incident is essential to determine the precise cause of the tingling sensation and to fully assess the potential for electrocution. Secondly, all damaged wires, especially the ground wire, should be promptly repaired or replaced to ensure proper insulation and protection. Thirdly, the grounding system should be meticulously checked to verify that it meets code requirements and provides a low resistance path for current to safely flow away from electrical equipment. Fourthly, ground fault circuit interrupters, commonly known as GFCIs, should be installed in areas where there is a heightened risk of electrical shocks, such as kitchens. GFCIs are designed to detect ground faults and trip the circuit, thereby preventing electrocutions. Fifthly, comprehensive training on electrical safety should be provided to all workers, emphasizing the dangers of exposed wiring and the importance of proper grounding techniques. A damaged ground wire poses a significant risk of electrocution because it compromises the safety mechanism designed to protect individuals from electrical shock. A ground wire's primary function is to provide a low-resistance path for electrical current to flow back to the source in the event of a fault. This path allows the circuit breaker to trip, cutting off the power and preventing a dangerous buildup of electricity. When a ground wire is damaged or corroded, its ability to conduct electricity is reduced, increasing the risk of electrocution. The presence of moisture further exacerbates this risk, as water is an excellent conductor of electricity, making the environment even more hazardous. An exposed ground wire in proximity to live wires can create a dangerous scenario where the ground wire becomes energized. This occurs when the insulation on a live wire is compromised, allowing electricity to leak onto the ground wire. If someone then comes into contact with the energized ground wire, they can receive a severe electrical shock, leading to electrocution. The severity of the shock depends on several factors, including the amount of current flowing through the wire, the duration of contact, and the individual's overall health. Grounding systems play a crucial role in electrical safety by providing a safe path for fault current to flow back to the source. A properly designed and maintained grounding system ensures that the resistance to ground is lower, allowing for quick and effective tripping of circuit breakers in the event of a fault. However, if the grounding system is not properly installed or maintained, it can become a hazard itself. High resistance in the grounding system can limit the flow of fault current, preventing the circuit breaker from tripping and increasing the risk of electrocution. This is particularly dangerous in environments where moisture is present, as water can further reduce the effectiveness of the grounding system. A tingling sensation in the hand is often an early warning sign of electrical shock and should not be ignored. This sensation is caused by the electrical current passing through the nerves in the hand and can be an indication that the body is being exposed to electricity. Even a mild tingling sensation should be treated with caution, as it can potentially lead to more serious injuries, including burns, muscle contractions, and even cardiac arrest. It is important to immediately investigate the source of the tingling sensation and take steps to eliminate the risk of further exposure. Investigating the incident thoroughly is crucial for determining the exact cause of the electrical shock and preventing future occurrences. This involves carefully examining the exposed ground wire, the surrounding electrical equipment, and the grounding system. It is also important to interview the person who experienced the tingling sensation to gather information about the circumstances surrounding the incident. By conducting a thorough investigation, it is possible to identify any underlying problems and take corrective actions to improve electrical safety. Repairing or replacing damaged wires is essential for maintaining electrical safety and preventing electrocution. This includes ensuring that all electrical wires, including the ground wire, are properly insulated and protected from damage. Damaged or frayed wires should be replaced immediately, and any exposed wiring should be properly insulated to prevent accidental contact. It is also important to regularly inspect electrical wiring for signs of wear and tear and to address any problems promptly. Checking the grounding system is a critical step in ensuring electrical safety and preventing electrocution. This involves verifying that the grounding system is designed and maintained according to code requirements and that it provides a low resistance path for current to flow away from electrical equipment. The grounding system should be inspected regularly for signs of corrosion, damage, or loose connections, and any problems should be addressed promptly. It is also important to ensure that the grounding system is properly connected to all electrical equipment and that the connections are secure. Ground fault circuit interrupters are life-saving devices that can prevent electrocution by detecting ground faults and tripping the circuit. GFCIs are designed to monitor the flow of current in a circuit and to detect any imbalances that may indicate a ground fault. If a ground fault is detected, the GFCI will quickly trip the circuit, cutting off the power and preventing a dangerous electrical shock. GFCIs are particularly important in areas where there is a high risk of electrical shocks, such as kitchens, bathrooms, and outdoor areas. Educating workers about electrical safety is crucial for preventing electrocution and other electrical hazards. This includes providing training on the hazards of exposed wiring, the importance of proper grounding, and the use of GFCIs. Workers should also be trained on how to identify and report electrical hazards and on the proper procedures for working with electrical equipment. By providing comprehensive electrical safety training, employers can help to create a safe working environment and prevent electrical accidents. In the context of the kitchen worker experiencing a tingling sensation while using a hose near an exposed ground wire connected to a steamer, it is plausible that the exposed ground wire played a role in the incident. Here's a detailed breakdown of why this could be the case. Firstly, the exposed ground wire might have sustained damage or corrosion over time, compromising its ability to effectively channel stray electrical currents to ground. This degradation could result from environmental factors such as moisture, cleaning chemicals, or physical wear and tear. Secondly, the proximity of the exposed ground wire to the steamer introduces the possibility of a live wire within the steamer making contact with the exposed ground wire. This contact can energize the ground wire, creating a pathway for electrical current to flow through the worker if they touch both the energized ground wire and a grounded surface, such as the wet floor. Thirdly, the overall grounding system of the kitchen might not be adequately designed or maintained. This could involve issues such as high resistance connections, inadequate grounding electrodes, or improper bonding of metallic components. A poorly maintained grounding system increases the risk of electrical shock by failing to provide a low impedance path for fault currents to flow back to the source, potentially diverting the current through a person. The tingling sensation experienced by the worker is a significant indicator of electrical current passing through their body. The severity of the sensation can vary depending on factors such as the voltage, current, path of the current through the body, and the duration of exposure. Even a seemingly minor tingling sensation should be treated as a serious warning sign of potential electrical hazard. Given these factors, a thorough investigation is essential. The investigation should include a detailed inspection of the exposed ground wire for any signs of damage, corrosion, or improper connection. It should also involve testing the grounding system to verify its effectiveness and compliance with relevant electrical codes. Additionally, the steamer should be inspected for any internal wiring faults or insulation breakdown that could be energizing the ground wire. Furthermore, it's crucial to assess the worker's condition and provide appropriate medical attention if necessary. The worker should be evaluated for any potential long-term effects of the electrical exposure, such as nerve damage or cardiac irregularities. In addition to the immediate investigation, several preventative measures should be implemented to mitigate future risks. Firstly, the exposed ground wire should be promptly repaired or replaced by a qualified electrician. This should involve ensuring that the new ground wire is properly sized, insulated, and connected to the grounding system. Secondly, the entire grounding system of the kitchen should be inspected and upgraded as necessary to meet current electrical codes and standards. This might involve installing additional grounding electrodes, improving bonding connections, or replacing outdated equipment. Thirdly, ground fault circuit interrupters should be installed in all areas of the kitchen where electrical equipment is used, especially near water sources. GFCIs are designed to quickly detect ground faults and interrupt the circuit, preventing electrical shocks. Fourthly, comprehensive electrical safety training should be provided to all kitchen staff. This training should cover topics such as the hazards of electricity, proper grounding techniques, the use of GFCIs, and the importance of reporting any electrical hazards. Fifthly, regular inspections and maintenance of all electrical equipment should be conducted to identify and address any potential problems before they can cause an accident. This should include visual inspections of wiring, testing of grounding systems, and preventative maintenance of appliances. By implementing these measures, the risk of electrical shocks and electrocution in the kitchen can be significantly reduced, creating a safer working environment for all staff. Firstly, assess the steamer and associated wiring for any insulation breakdown, loose connections, or signs of wear and tear. Use appropriate test equipment, such as a multimeter, to check for voltage leakage from the steamer's internal wiring to the exposed ground wire. Secondly, evaluate the grounding system's impedance. Use a ground impedance tester to measure the resistance between the grounding electrode and various points in the electrical system, including the exposed ground wire. High impedance indicates a compromised grounding path. Thirdly, check the continuity of the grounding conductor. Use a multimeter to verify that the ground wire is continuously connected from the steamer back to the main electrical panel's grounding bus. Any breaks or high resistance connections can impair its effectiveness. Fourthly, inspect the wiring for proper gauge and type. Ensure that the ground wire is of the correct size as specified in the electrical code for the steamer's current rating. Undersized or inappropriate wiring can overheat and fail. Fifthly, check the overcurrent protection. Verify that the circuit breaker protecting the steamer is appropriately sized for the appliance's current draw and that it trips correctly under fault conditions. An improperly sized breaker may not trip quickly enough to prevent a shock. Sixthly, inspect the environment for contributing factors. Assess the presence of moisture, conductive surfaces, or other conditions that may increase the risk of electrical shock. Address any such factors promptly. Seventhly, analyze the worker's experience. Gather detailed information about the tingling sensation, including its location, intensity, and duration. This information can help determine the potential path of the electrical current and the severity of the exposure. Eighthly, document all findings. Record all observations, measurements, and test results meticulously. This documentation will be crucial for identifying the root cause of the incident and implementing appropriate corrective actions. Ninthly, consult with a qualified electrician or electrical engineer. Seek expert advice to evaluate the findings and develop a comprehensive plan for addressing any electrical safety issues. Tenthly, implement a comprehensive preventative maintenance program. Establish a schedule for regular inspections, testing, and maintenance of all electrical equipment and systems to prevent future incidents. The NEC, or National Electrical Code, provides specific guidelines for grounding and bonding to ensure electrical safety. Some relevant sections include Article 250, which covers grounding and bonding requirements for electrical systems, and Article 430, which addresses motor circuits, including those used in steamers. The NEC emphasizes the importance of a low-impedance ground path to facilitate the clearing of ground faults. Section 250.4 specifies the requirements for grounding electrical systems, including the size and type of grounding conductors. Section 250.96 requires bonding of metal enclosures to ensure electrical continuity and prevent voltage buildup. Section 250.166 provides guidelines for sizing grounding electrode conductors for different types of grounding electrodes. Article 430 addresses the grounding requirements for motor circuits, including the need for a separate equipment grounding conductor run with the circuit conductors. NEC Table 250.122 provides guidance on the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. GFCIs are required in many locations to protect against electrical shock hazards. NEC Section 210.8 specifies the locations where GFCI protection is required, including kitchens, bathrooms, and outdoor areas. GFCIs are designed to trip when they detect a ground fault current of 6 mA or higher. They are very effective at preventing serious electrical shocks. Regular testing of GFCIs is recommended to ensure that they are functioning properly. The manufacturer's instructions should be followed for testing procedures. Most GFCIs have a test button that can be used to simulate a ground fault. Electrical safety training should cover the following topics: the hazards of electricity, including the risk of electrical shock, burns, and electrocution. Proper grounding techniques, including the importance of a low-impedance ground path. The use of GFCIs, including how they work, where they are required, and how to test them. Lockout-tagout procedures for safely de-energizing electrical equipment before performing maintenance. Proper use of personal protective equipment, such as rubber gloves and safety glasses. Safe work practices for working near electrical hazards, such as maintaining a safe distance from energized equipment. Emergency procedures for responding to electrical accidents, such as how to shut off the power and provide first aid. By adhering to these guidelines and recommendations, the risk of electrical shocks and electrocution in the kitchen environment can be significantly reduced, ensuring the safety and well-being of all workers.